Hello everyone, I'm Prantarkash from Dartmouth College and I'm going to talk about new verification schemes for frequency-based functions on data streams. Let me begin with the problem and motivation. So let's say we are getting a huge data stream where elements are getting inserted and deleted continuously over time. And we are asking statistical questions such as how many distinct elements do we receive, what is the maximum frequency of an element, what are the frequency moments, most frequent elements, and so on. These questions have been extensively studied since the beginning of the study of data streaming algorithms, and it is known that if we do not have enough space to store all the frequencies, then it is provably impossible to exactly compute such properties. Therefore, we need to settle for approximations. However, we ask if it is possible to exactly solve them in space sublinear in the universe size by slightly enhancing the model. One such enhanced model was defined by Chakrabarty et al. In ICAR 2009 called the Annotated Streaming Model. Here, a space-restricted client has a data summary and he has hired a cloud service with unbounded memory to do the computation for him. So the client receives a stream token, updates his summary, and uploads the token to the cloud. And they go on doing this, and therefore, at every point, the client ends up with a summary of the data, while the cloud has the entire data in store. Now, when solving a problem on the data, the client asks the cloud to do the computation for him and send the answer. However, the cloud might have been hacked, or it might have incurred some hardware or network failure, and therefore, the client doesn't want to blindly trust it. So this becomes a prover verifier system where the cloud, the prover, sends a help message or proof to the client, the verifier, in support of its answer. Now with the data summary the client has stored, he does some computation and verification and then outputs an answer if he thinks that the cloud was honest, otherwise rejects the proof. In such a protocol, the complexity parameters that we should try to optimize are the length of the proof and the space used by the verifier. Now let me make it a bit more formal. So a scheme is a protocol between prover and verifier, who are sometimes called Merlin and Arthur, following a long-standing tradition in complexity theory. They read the input stream together. Prover stores the entire data, while verifier stores a relevant part of it. After that, prover sends a help message or proof to verifier, who processes it with his limited space, and then outputs an answer if the proof he thinks that the prover was honest, and otherwise rejects the proof. A scheme should satisfy the following two properties. It should be complete, which means an honest prover should be able to convince the verifier to output the correct answer with high probability, and it should be sound, which means a verifier should be able to catch a cheating prover with high probability. A small error probabilities with which completeness and soundness might fail are called completeness error and soundness error respectively, and we aim for them to be at most 1/3 usually. Another terminology I'd be using throughout the talk is that of H, V scheme, which refers to a scheme with order H bits of help, that is H cost in short, and order V bits of verification space, which is V cost in short. Okay, now I'll define the main problem formally. So let's say we have a stream on the universe 1 to n, and a frequency of the jth element is denoted by fj. Then a frequency-based function, capital G of this frequency vector f, defined as summation of small g of fj with j running from 1 to n for some predetermined function small g, is a frequency-based function. Now let's look at some concrete examples to make it more clear. So let's say if we define gx as 0 when x equals to 0 and 1 otherwise, then note that capital G of x is nothing, capital G of f gives nothing but the number of distinct elements, that is the 0th frequency moment f0. If we define gx as x power k for some positive number k, then gf captures just the kth frequency moment fk. And we can also define the gx to be 0 if x is less than or equal to some number capital M and 1 otherwise, to see that gf is equals to 0 if and only if M is the maximum frequency of an element, that is f infinity. So these are some examples of frequency-based functions. Now, Chakravarti et al. Gave a scheme for any general frequency-based function with proof size and verification space, both n power 2/3 times log n power 4/3. It's an involved scheme with integrated data structures and an elaborate framework for identifying the heavy hitters called hierarchical heavy hitters. And also the direct application of this scheme is the best known ones for the important special cases of computing f0 and f infinity. This brings me to our results. We give a scheme for any general frequency-based function with proof size and verification space n power 2/3 times log n. So we improve upon this log factor. And more importantly, the scheme is simple, using some basic sketches and summaries, such as the Misra-Gries summary, which we use for identifying the heavy hitters. And so our result consequently improves the best known bounds for these important special cases of f0 and f infinity in particular. Now I'll give you an overall picture of our scheme, and then I'll move on to details. So the generic idea is very simple. So what the verifier does is it runs a streaming algorithm known in the basic streaming model, that is without the prover, to partially solve the problem. And then for the remaining unsolved part, he takes the prover self. So this is kind of where our scheme wins over the previous best scheme, because there the prover was mostly doing all the work. Okay. So in particular for our problem, the verifier uses an algorithm to get good estimates of the frequencies and so that he can identify the heavy hitters, that is which we define here as the elements with frequency more than n power 1/3. So there can be at most order n power 2/3 many heavy hitters, and prover then sends the exact frequency of these elements. So it takes communication n power 2/3 times log n to send them, and we show that these frequencies can also be verified in n power 2/3 times log n space. Now, once we verify these exact frequencies, we can easily compute their contribution to capital G of f. Now we turn to the light hitters, that is the elements with frequency at most n power 1/3. We show that the prover can send a n power 2/3 degree polynomial, which can be summed over different values to obtain their contribution to capital G of f. And because this polynomial has degree n power 2/3, it can be expressed with n power 2/3 times log n bits. And we show that it can be verified with these same bits of space. So now that we have both the contributions, we can just add them up to get our desired value, capital G of f, and we see that the overall proof size and verification space is n power 2/3 times log n as claimed. So this was the overall picture, and now I'll go into details. As mentioned before, we use the classical and fundamental algorithm Misra-Gries, given by Misra and Gries in 1982 for the frequency estimation. It's a simple algorithm given as follows: that given a stream of length m and a parameter phi, it allocates space for phi inverse keys, many keys, and keeps corresponding counters. When an element is inserted, it first sees if the element is already in the keys, and then it increments its counter by 1. Otherwise, it first checks if there is space for more keys, then it adds this element to the keys and sets its counter value to 1. And otherwise, if there is no space for more keys, it decrements the counter value of each of the current keys. And if some counter value becomes 0, it removes that element from the keys. So this is the main algorithm. And finally, the estimate returned is the count of the estimate of an element is its counter value. And it's thought to be 0 if the element does not belong to the keys. So I describe this algorithm in details because these keys and this property is something that we will actually use in our scheme. So Misra and Gries proved that this algorithm gives an estimate as follows. We never overestimate, and we underestimate by at most an additive factor of 5 times m. So, and the space usage of phi inverse times log n is immediate. So one issue is that we see that this works only for insert only strings, but we would want our scheme to work for turnstile strings, that is with both insertions and deletions. Therefore, first we need to extend it to turnstile strings, and this extension is easy. So we call this the extended Misra-Gries or EMG algorithm in short, where we process the insertions and deletions in separate parallel copies of the Misra-Gries summary. Now we would get a total estimate of the total positive update. Let's call it fj hat plus, and an estimate for the total negative update. Let's call it fj hat minus. Now, then subtracting this fj hat minus from fj hat plus will give an estimate of the actual frequency, and here we can easily show that this frequency estimation varies from the actual frequency by an additive factor of phi m, and this time we can also overestimate, but only by this additive factor of phi times n. And the space usage is asymptotically same as before. So with this estimation lemma in hand, we move on to describe our scheme. So recall that our goal is to compute this function capital G of f, we defined as summation of small g of fj, j running from 1 to n, where small g is some function known to us. Now, what we do first is that note that we work with streams of length at most some constant times n. So previous work has also solved the problem for these type of streams. And then the verifier runs this EMG subroutine setting phi to be 1 over this capital C times n per 2/3. With this setting, by this lemma, we see that in order n per 2/3 times log n space, we would get estimates such that they would vary from the actual frequency by an additive factor of at most n per 1/3. Okay. So then we note that if an element does not belong to the keys of the EMG algorithm, its estimate is 0, and so its actual frequency, its absolute value is at most n per 1/3. This is something we would use in our later. So now, as mentioned before, we would split this summation into the contribution by the keys and the contribution by the non-keys. So let's look at the contribution by the non-keys first. So recall that from the last slide that we know that if for the non-keys, they have the absolute value of their frequency is at most n per 1/3. So let's call their contribution as LH, short for light heater, and this is given by the summation. Now we would want this summation to be over 1 to n. So what we just do is simply multiply this quantity by an indicator function h of j, which is 1 if j does not belong to keys and 0 otherwise. So now we have the summation over all j in 1 to n. And once we have this, we convert it into a double summation as follows. We shape this n-length one-dimensional vector into a two-dimensional n per 1/3 cross n per 2/3 array. So an index j in 1 to n here now becomes a pair x comma y, where x comes from 1 to n per 1/3 and y comes from 1 to n per 2/3. So this is for the double summation we get, and this is called as the shaping technique, which is pretty popular in this area, and it's on a high level it's used to distribute the work between the prover and the verifier. Okay, once we have done this shaping, recall that we are looking for a polynomial encoding of the value we are looking for, but these are not yet polynomial functions. So what we do is use Lagrange's interpolation to get polynomials g tilde, f tilde, and h tilde, which agree with g, f, and h at all values in their domain. for over this finite field, large enough finite field, capital F. So we call these polynomials as capital F extensions of G, F, and H. And once we have them, we can simply replace G, F, and H by G tilde, F tilde, and H tilde. So now these are polynomial functions, and therefore we can define this polynomial P of X in such a way that the inner summation is captured as a polynomial function of each x in this outer summation. So basically what happens is that the quantity we are looking for, L8, it becomes just a summation of this polynomial P of X, where x runs from 1 to n power 1/3. And now let's look at the degree of this polynomial P. Well, the degree of G tilde is order n power 1/3 because we ensured that its domain has size order n power 1/3. And we also see that the degree of this variable x in the polynomials f tilde and h tilde are also n power 1/3. Therefore, what we get is that because of this G tilde composed f tilde factor, the degree of P is order n power 2/3. Okay. So the takeaway from the last slide was that we have this polynomial P of X defined in such a way that the quantity we are looking for is just summation of Px, where x runs from 1 to n power 1/3, and the degree of P and consequently its number of monomials is at most n power 2/3. Okay, so what the verifier does is that first he runs EMG with phi equals to 1 over c times n power 2/3 as mentioned before, and then he picks an element in this field F uniformly at random. Now, looking at the keys in the EMG subroutine, he constructs h tilde of r comma y for all y in 1 to n power 2/3. Recall that h tilde depends only on the key values. Okay, next, as the stream arrives, he maintains with the stream updates values f tilde of r comma y for all y in 1 to n power 2/3. And it is known from prior work how to maintain these values dynamically with the stream outputs. Now the prover would send the verifier a polynomial p hat that is claimed to be identical to p. And as the verifier receives the proof, he computes p hat of r. And also he computes P of R using this equation. Note that he has all the necessary tools, these f tilde ry and h tilde ry values, to compute P of R. So now that these are computed, he checks if they are equal, P of R is equal to P hat of R, and if yes, he believes that P and P hat of are identical, and so using equation 2, he computes LH as summation of P hat x extending from 1 to n power 1/3. So now this completes the description of the protocol, and now we do the analysis. So completeness is immediate because by this math, if the prover is honest, we'd always output the correct answer. So it's perfectly complete. And as for soundness, it might be that P was actually not identical to P hat, but this check PR equals to P hat of R passed, and so our protocol failed. But this can happen only when R is a root of this polynomial P minus P hat, and that has probability at most degree of P, which is n power 2/3 as noted before. So taking this field to be large enough size, large enough poly of n, we bound the soundness error by at most 1 over poly n. Now for the cost analysis, note that now number of monomials of P was order n power 2/3, and so to express this, we would need n power 2/3 times log n's bits, because each of the coefficients come from this field of size poly n, so the coefficients have size log n. And we maintain 2 field elements for each of these n power 2/3 values, and each field element has size log n. So the V cost is also n power 2/3 times log n. Okay, so now that we are done with the non-key contributions, let's look at the key contribution. One is intended. So let's call this value as HH, short for heavy hitters. This is the expression for their contribution. So what the prover does is he sends values f prime j for all j in keys and claims that they are identical to the actual frequencies fj. Note that if we can just verify the correctness of these values, then because we know g, we can easily calculate hh. So all it remains is to go verify these values, and that's why we define this quantity capital T as summation of fj minus fj prime whole squared, where the j runs over all the keys. Note that this quantity T is 0 if and only if fj and fj prime are equal for each j. So now, just like before, with these shaping techniques and Lagrange interpolation, we can express this as a sum over polynomial q of x, where x runs from 1 to n power 1/3. We skip the details, but this is what we'll get, and the degree of q would be order n power 1/3. So now we check if t, calculate the value of t and check if it's equals 0. And if it is, we believe that these values are equal, and we simply calculate hh by summing g of fj prime over all j in keys. So we had the calculate the LH before, and we now have the contribution of the heavy hitters hh. We sum them up to get our desired quantity, capital G of f. So first, for the h cost, note that there were order n per 2/3 many keys, and so the h cost is order n per 2/3 times log n for communicating these frequencies. And for this sub protocol, we would incur h cost of n per 1/3 times log n because q has this degree, and we can show that the v cost would be also n per 2/3 times log n. So overall, we get n per 2/3 log n, n per 2/3 log n scheme. So our main theorem basically says that we have a scheme with both proof size and variance space n per 2/3 times log n for any frequency-based function in any turnstile stream of size length order n. As direct corollaries, we see that there is a schemes with the same complexity bounds for computing f0 and f infinity, and also checking multiset inclusion, that is whether a multiset X is contained in a multiset Y, both of whose elements are coming in interleaved streaming order. This is an important subroutine for various problems such as graph problems. And we note that we improved the previously best known bounds for each of these problems. Now I'll briefly tell you how we can handle longer streams at the cost of imperfect completeness. So our last scheme required string length to be order n, but and Chakraborty et al. Scheme also assumed the same, but it works for longer streams as long as the L1 norm of the frequency vector is order n. So we can have massive cancellations, but the total mass of the stream is restricted to at most constant times n. So we no longer can use the EMG algorithm because it doesn't give us a good estimation with respect to the L1 norm of f. However, we can use the count median sketch given by Cormor and Muthukrishnan, which gives us a similar estimation, but with respect to the L1 norm of f. And with a bit more work and some modification, we can see that we get a scheme with the same complexity bounds for any frequency-based functions for any turnstile streams that satisfies this norm 1 of f is order n. However, for this scheme, we would incur a non-zero completeness error because the count median sketch is randomized, unlike Misra-Gries. So it can make an error, and then even if the prover is honest, we might think that he is lying and our protocol might fail. So to summarize, we gave new schemes for frequency-based functions, which are simpler than previous schemes and improves the complexity bounds. It also improves the base known bounds for the important special cases of f0 and f infinity. We give perfectly complete schemes for when the stream length is order n, and our protocol also works for longer streams at the cost of imperfect completeness, and our high-level idea is generic enough to be applicable for other problems. I'll wrap up with some open questions. So a natural open question is whether we can close the gap between the upper and lower bounds. So our upper bound says the max of h cost and v cost is n per 2/3, while an Lower bound given by Chakraborty et al. Says that their product is at least n, and so the max should be at least square root n. So there is this gap, square root n and n for 2/3, and we ask that even if not for the general case, can we at least get better upper bounds for special cases of f0 or f infinity? What about even if we relax the model, which is the prescient model, where the prover knows the entire stream upfront and can give help messages accordingly? Can we get better upper bounds for that? And finally, if we ask if we can get stronger lower bounds than h times v at least n, and success here would make progress towards solving this long-standing open question in MA communication complexity about breaking this square root n barrier. With that, I'd like to end. Thank you for listening.